Projectiles, inclined plane, type 4, landing angle. So up until this point we were looking at how the particle was landing either vertically or horizontally. So in this example today we're going to focus in on the actual landing angle itself when it's not landing vertically and when it's not landing horizontally. So here we're given from a point P on a plane inclined at tan inverse of a half to the horizontal. A particle is projected with a speed of 30 or view at 30 degrees to the plane. The motion takes place in a vertical plane through the line of greatest slope. In other words, it's not veering off to the left or the right when it's travelling up the plane. And we have to find the tan of the angle. Okay, so what are we given? We're given the angle of the plane itself. We're given the angle of projection with respect to the plane. And we're asked to find not the angle, but instead tan of the angle when it is landing. So let's sketch this and see what's happening in this diagram so we can break it down. So this angle here is tan inverse of a half. And then we have projected with a speed of u at an angle of 30 degrees. And then we have on landing. Okay, so it's important to remember that when it's landing, here we have our velocity coming in on landing. So that's our v. This will be our landing angle, L. But of course, if we resolve that, I'm going to use a different colour for resolving my velocity vector there then. We can see that v in both directions, in the x and the y direction. And if I resolve my initial velocity vector, you can see u in the y direction and u in the x direction. Which doesn't look very like right at 90 degrees there, does it? Let's just get rid of that there for a second. So it should be at 90 degrees there. Okay, so that's better. So that's u in the y direction and u in the x direction, where this is u, the resolved vector. So we can see that v in the y direction is in the opposite direction, so therefore that's going to be negative because it's in the opposite direction to the initial velocity, whereas v in the x direction is going in the same direction as u of x, and therefore will be the same sign, so i.e. positive. Okay, so we know that on landing, let me just get rid of all this extra dots here. On landing, we have our landing angle, but we also have sy will be equal to 0. So the first thing before I may get my table is I want to deal with this tan inverse of a half. So normally we say our angle with respect to the plane is alpha and our angle of the inclined plane is beta. So in other words, beta is equal to tan inverse of a half. In other words, tan beta is equal to a half. And if we make our little right angle triangles, there's beta. Then we have opposite over adjacent, and therefore the hypotenuse is going to be the square root of 5. So now I can get sine and cos of beta. So we can say therefore sine beta will be equal to our opposite over hypotenuse, 1 over root 5. And cos beta will be equal to our adjacent over hypotenuse, in other words, 2 over root 5. Okay, so now we've dealt with our angles. We might also want to note that alpha is 30 degrees, so therefore sine alpha is going to be sine 30, which is a half, and cos alpha will equal cos 30, which is root 3 over 2. Okay, so that'll come in useful when we're filling in our tables. Okay, so in order to find tan of the angle as it meets the plane, well, essentially what are we looking for there? Well, we're looking for tan of the landing angle. And we have to remember the key to this question then is going to be the tan of the landing angle is minus Vy over Vx. So in other words, if I can find Vy and Vx, it's going to be very easy to find tan of the landing angle. But of course, to find Vy and Vx, we're going to need time. And to get our time, we'll be looking at Sy is equal to 0. So I'm going to get you to pause the video, and then you're going to fill out your U, A, V, S and T table with respect to X and Y. Okay, so U in the X direction is always U cos alpha, so we have to remember that our U vector is U cos alpha in the I direction and U sine alpha in the J direction. So of course you can write this table in terms of I and J there, it doesn't matter if you prefer X or Y or I or J. So U cos alpha in the X direction, well, we saw the cos alpha is root 3 over 2, so therefore that's going to become root 3U over 2. And in the Y direction it's U sine alpha, so therefore that's going to be U times a half, in other words U over 2. A, our gravity vector, has to be resolved, and of course we've seen in our previous examples that it's going to be minus G sine beta in the X direction, and sine beta is 1 over root 5, so that's going to be minus G over root 5. And A, or G resolved in the Y direction, is minus G cos beta, so this is going to be minus 2G over root 5. So therefore we know that V is equal to U plus AT, so therefore in the X direction that's root 3U over 2 minus G over root 5T, and in the Y direction, well, that's going to be U over 2 minus 2G over root 5T. S in the X direction, well, S is UT plus a half AT squared, so that's root 3UT over 2 minus G over 2 root 5, and remember it's T squared. And then S in the Y direction, well, that's UT over 2, and again minus a half is going to be G over root 5 T squared, and T is obviously with respect to T. Okay, so as we said there, in order for us to find our landing angle up here on the right hand side, well, what are we going to need? We're going to need our Vy and our Vx, and if we look at our table here, we need our time of flight in order to do that. So we also know that on landing, Sy is equal to 0. So we're going to start with our Sy is equal to 0, where Sy was Ut over 2 minus G over root 5 T squared. So if I let all of that equal to 0, I'm going to get rid of my fractions first. So I'm going to multiply across by 2 root 5. So in other words, I'm going to have root 5 ut minus 2 gt squared is equal to 0. Highest common factor is t, which leaves me with root 5u minus 2gt is equal to 0. And of course, in factorising, if both multiply to give us 0, that means that one must equal to 0, or the other must equal 0, or both must equal 0. So if I get t on its own, then I end up with root 5u over 2g. And of course, t equals 0 at the start. In other words, sy is equal to 0 at the starting point here and also at the landing point. Okay, so there's 2 times where our displacement above the plane is 0. So therefore, root 5u over 2g, I should say, is our time of flight. Okay, so now we have our time of flight. It's very easy because the next thing we need to do, of course, is get tan of our landing angle. And tan of our landing angle is equal to minus Vy over Vx. Okay, and that's on landing. And therefore it'll be at the time of flight. So we can do one of 2 things. We can sub Vy and Vx straight into the equation all in one go, or you might prefer to work out Vy and Vx separately and then sub it into the equation. Okay, so I'm going to just work out Vy and Vx separately here, just to break it down for you. So we have Vy is equal to u over 2 minus 2g over root 5t. Okay, and of course our time of flight we have to sub in. So we have minus 2g over root 5. That minus shouldn't be there. and that's going to be by our time of flight, which we said was root 5u over 2g. So nice and handy there, because 2g is gone and root 5 is also gone, which leaves us with a nice simple equation then of u over 2 minus u. So therefore Vy is equal to minus u over 2. So as we expected, obviously the velocity would be negative. Okay, so our Vx then, if we go back, was root 3u over 2 minus g over root 5t. So again, if we sub in our time of flight, well, we have root 3u over 2 minus g over root 5 times our time of flight, which was root 5u over 2g. So again, one of our g's is cancelled and root 5 goes into root 5 once. So therefore that leaves us with root 3u over 2 minus u over 2. And then if I simplify that, I end up with root 3 minus 1 times u all over 2. So we have our Vx and we have our Vy. So then if I sub that into my landing angle, we say therefore tan of the landing angle is equal to minus Vy. So minus u over 2 is just going to become u over 2 divided by root 3 minus 1 over 2 times u. So of course if I turn that upside down and multiply, my 2's are going to cancel and my u's are going to cancel. So in other words, u goes into u once and 2 goes into 2 once. And of course then what does that leave us with? Well, it leaves us with tan of the landing angle is equal to 1 over root 3 minus 1. Okay. Now you could, of course, simplify by multiplying above and below by your conjugate there. So the other way in which we could write that answer is if I multiply the top by the conjugate, which would be root 3 plus 1, and I multiply the bottom by the conjugate, which would be root 3 plus 1, and therefore tan of my landing angle would be equal to root 3 plus 1 over root 3 by root 3, which is 3, plus root 3 minus root 3 is 0 and minus 1. So therefore tan of my landing angle could also be written as root 3 plus 1 over 2. Okay, so both of those answers would be tan of our landing angle. Okay, so what I'm going to get you to do now is just one question, and that is the 1993 question 3 question that I've posted below this video, okay?